Let's take a look at the six-membered ring here. So if I take 6 carbons, that'd be cyclohexane, hex means 6. And the six-membered ring, if I try to put all the carbons in the same plane, what do I notice here? Well, the bond isn't quite lining up with the hole on the neighboring carbon. It doesn't really want to connect itself when I make them all in the same plane. And that's because if I were to create a six-membered ring and all the carbons were flat in the same plane, the angles would be 120, which is not the correct angle. It's not 109. So it's not going to be as stable if it were flat. So I'm never going to really see a flat six-membered ring, maybe for a second, but not for any significant period of time. And I can see that if I try to make it flat, the model kind of resists that. It's hard for me to keep all the atoms in the same plane. So if a six-membered ring, cyclohexane, were flat, again, there's no double bonds in here, it's all single bonds, it would be unstable. It would have angle strain. So the angles are 120. Should be 109. So wouldn't expanding the angles to an even larger value create even less repulsion between them? Well, that's true, but if I expand the angles between the carbon-carbon bonds on the inside of the ring to 120, that really pushes the electrons out and they get too close to the CH bond. So those angles are now not as large as they should be. They're smaller, and that causes repulsion there. So any deviation from the angles we expect for an sp3 hybridized carbon, which is 109, is going to cause a little repulsion, even if the angles get farther apart, alleviating repulsion there. They're only going to get closer together over here, causing some more repulsion between the C and CH bonds and the two CH bonds here on the outside. So the optimal angles are 109. That allows everything to spread out as much as possible. So this is unstable because of angle strain if the ring is flat. If it's flat, I also see, again, just like the other flat rings, it's really unstable because of the eclipsing of the CH groups on adjacent carbons. So how do I make this into the chair, which is the most stable conformation for cyclohexane? To make your flat structure into a chair, put your fingers on every other hydrogen on one side of the ring, and then put your fingers on the other hydrogens on the other side of the ring, and then just pull those gently towards yourself. And you'll see it's now no longer flat. Now I've got this kind of zigzag in the backbone of my ring. And that's meant to kind of look like a chair, where here's the base of the chair. My little guy's sitting right here. His feet are down here, and his head gets to rest up here on the top. He's just hanging out in that chair there. So the chair conformation is quite stable. There's actually no ring strain in here at all, right? We said ring strain consists of angle strain and torsional strain. And all of that is alleviated with the chair. So a given cyclohexane molecule almost always exists in the chair conformation unless it gets hit by something and kinetic energy causes its bond to rotate. So what are the advantages of the chair conformation? Well, by doing what we did and making the ring so it's not flat, now all of these angles are actually 109. They're perfect. There's no extra repulsion due to the electron groups on the same carbon getting too close together and repelling. And if we go back to the flat structure again, as you're trying to make it flat, you'll kind of feel the molecule resist that because the angles are 109. It's more stable at 109. And when I take my fingers and put them on every other carbon on this side and then every other carbon on the opposite side and pull that together, I can feel the molecule relaxing. It's actually loosening up because I'm alleviating some of that angle strain, or all of the angle strain, because now the angles are 109.5. What else do I notice about this? It's fully staggered all the way around. I could take any two carbons and eclipse them, and the hydrogen on one is staggered right between the two hydrogens on the other, right? I can rotate this anywhere I want. The hydrogen on the front, carbons are staggered right between the two on the back. Same thing here. This hydrogen staggered between those two atoms. So it's fully staggered all the way around. There's no eclipsing of atoms on adjacent carbons, so there's zero torsional strain. What makes this a little bit unstable, the only thing that's really unstable about it, is the so-called 1,3 diaxial strain. And so when we look at this cyclohexane ring, what we see is three of my hydrogens pointing like straight up off the ring, and three underneath pointing straight down. Some of these are kind of pointing out and down a little, or out and up a little. So the ones pointing straight up are called axial hydrogens. Those are the ones I'm touching with my fingers. And the ones pointing out to the side a little bit down or a little bit up are called equatorial hydrogens. So the 1,3 diaxial strain, which is different from torsional strain, is the only thing that really is making this unstable. These hydrogens on top of the ring have clouds that repel. They're a little bit too close together up here. That makes it a little bit unstable. It's not torsional strain because the hydrogens we're talking about are not on adjacent carbons. The hydrogens on adjacent carbons are all staggered. The hydrogens on carbon 1 and 3, those are the ones that are both axial and they're repelling a little bit. So 1,3 diaxial strain is on carbons, every other carbon. Torsional strain is on adjacent carbons, so it's a slightly different thing. And so this is a chair. It's the most stable conformation for cyclohexane. The book also talks about something called a boat. So if you have a chair, you can make it into a boat. You can also make a boat from a flat structure. So if I have a chair already, I can kind of find my 4 flat carbons. I've got the head of the chair and the feet down here. All I have to do is bring the feet up to the same elevation as the head. And I'll pull the head and the feet together. And that makes a little boat. I've got like a canoe, the base of the boat, and either side is kind of coming up. And that creates the boat conformation. So this is not nearly as stable as the chair. And what are the reasons for that? Torsional strain and something new called flagpole interactions. So if I imagine this is a boat that's sitting on the water, I've got these 2 hydrogens that point kind of up and actually in toward one another a little bit. So clearly you can see they're a little too close. Their electron clouds are going to repel. Those are the flagpole interactions. Those are actually on carbon 1, 2, 3, 4. Carbons 1 and 4, the hydrogens that point toward one another, or if those are other groups, they'd be even more repulsive because the electron clouds would be even bigger and they'd repel even more. That makes the boat pretty unstable. It's not as unstable as the flat ring though, because it doesn't have any angle strain and it only has a little bit of torsional strain in addition to the flagpole interaction. So where's the torsional strain? On the underside of the boat. These 2 carbons here in the same plane, notice they're pretty much eclipsing. The hydrogens are not staggered. Their electron clouds are a little too close on adjacent atoms. So when the electron clouds are too close because they're eclipsing on adjacent atoms, that's when I have torsional strain. So it's torsional strain here, down here, and then on the other side here, and also over there. So there's 1, 2, 3, 4 torsional strain hydrogen-hydrogen interactions in addition to the flagpole interactions. That makes the boat a little bit less stable, significantly less stable than the chair.